Okay, from now and the next few videos will be one of my favorite topics. It's something called algebraic method in enumerative combinatorics. So what we are doing here is called combinatorics. More precisely, is enumerative combinatorics. So this is the fancy jargon, basically means counting. We list the things. And then algebraic method means we're going to use algebra. Okay, what algebra? Algebra means solving equations. So we are going to use polynomial to solve. Okay, so the point is, we have learned so many counting techniques. They are so messy. These ideas are scattered. They are not linked. It's not systematic. Then naturally, is there a more systematic way to counting? Yes. And the idea is algebraic methods. So recall in the very beginning, in the video 1, okay, video 1a, we have performed the manually how to perform the inclusion-exclusion principles on 2 sets, 3 sets, and 4 sets. And we have counted the number of single term, double term, triple term, okay? So just an revision. So AUB is A plus B minus A and B. Okay, so 1 single term, 2 single terms. So this is a 2 here, and this is a 1 here. Okay, so this is an example. And then what about 3 sets? So how many single sets? 3. Oops, 3. How many double sets? 3. How many triple sets? 1. So that's the number. And we also know that from binomial theorem, if we expand this expression, we will have these kind of numbers. And you see a thing. These two numbers, what? They are the same. That means what? That means there is a bijection. And that means what? By the idea that if there is a bijection and counting x is complicated, so we can count y instead. So that means what? That means we can count this using this. So this is actually how you count. For what? For let's say if I have union from 1 to 100. I have 100, that means A1 or A2 or until or A100. So it will be a mess, a lot of terms, right? How many terms are there? Well, we can actually think of it as 1 plus x to the power 100, and then you expand the terms. Then you can use it to count, for example, how many double terms? How many double terms? It will be 100 C2, right? How many 10 terms? It will be like this. So why it works? Because there is a bijection. That means counting x is difficult. We can use y to count it. So what's the powerfulness? So now we are going to give you some example how this is powerful. For example, I have an A, B, C, 3 numbers, integer. Z plus means positive integer. That means positive 0, 1, 2, 3, and so on, cannot be negative. And now I'm saying that A has to be between 2 and 5. B has to be between 3 and 6. And C has to be between 4 and 7. That means A can only be 2, 3, 4, 5. B can only be 3, 4, 5, 6. C can only be 4, 5, 6, 7. Okay? So how many ways can we have A plus B plus C equal to 17? Wow, how are you going to count this? Magically, the solution will be, it is the coefficient x17 in this polynomial. And let me recap, I will use this notation to mean coefficient of x17. Okay, so basically the solution to this problem will be, if I want to write down, it will be x17 like this. Okay, and then now we are not going to talk about how we solve it yet, but this is to illustrate. We can actually solve this problem by using polynomial. Okay, we will talk about how to solve this later. Okay, now another example. You distribute 8 identical cookies among 3 children. So we have 3 children, and each children can receive at least 2 cookies and no more than 4 cookies. How many ways can you distribute? So you have, the answer will be, magically, it will be x8 to this polynomial. And let's think about how can you solve this problem in the classical sense. You have 8 cookies, so, and then you have 3 children. So children 1, children 2, children 3. So now I'm saying each children receive at least 2 cookies and no more than 4 cookies. So that means what? That means at least a cookie I have to select 2, and this go to children 1, and then but for children 1 I can also have 3 cookies, and I can also have 4 cookies, right? So these are all the number of cookies I can have for children 1. This is only for children 1. But under this situation, if I have a cookie distributed to children 1, how many cookies left for children 2 and 3? I have 6. So for the remaining 6 cookies, I can have, let's say, 2 cookies for children 2, or 3 cookies for the children 2, or 4 cookies of the children 2. And again, now you see where I'm going. If I distributed 2 cookies to children 2, what about the remaining cookies for children 3? There will be 4 cookies for children 3. That means what? There will be 2, 3, and 4 ways to distribute the cookies for children 3. I'm now drawing a tree. So I have 3 boxes. The first branches is I distribute 2 cookies for the children 1. That means I have how many ways? I have 8, 2 for the first way. Then now for the remaining branches, I have what? Also 2 cookies for the second children. So I will have what? 6, 2. Okay, and I can go on. And then if I go this way, I distribute 3 cookies for the first children, then I have 3. Okay, I can go on. And if I distribute 4 cookies for the first children, I have what? 4. Okay, and I can go on. And now I have a very big tree. And in the end, the final outcome will be all the possible way I can distribute for the cookies and have sum all those numbers together. It's very painful. But instead, now I'm telling you, you just need to expand this polynomial and find the coefficient of xh in this polynomial, and that's the answer. This is much more easier to do, okay? And of course, you may wonder, how come? How come we can now escape from this messy, complicated analysis, and now we suddenly have a very powerful magic formula? Well, because there is a bijection between the problem and the polynomial coefficient.